styles of formal verification. So that is the second guest lecture. The third, which is maybe a highlight of this, is so as you will see in when I get into detail, Lean is what is called a functional programming language, and functional programming languages are easy to reason about. So that's great. You have a functional programming language, you reason about it, and you prove theorems about it. Except that in the real world, for various reasons, either optimization or verifying Rust or Python or some other code by compilation or whatever else, you're forced to go to monadic verification, where your program is what is called imperative. As we get into details, we'll see a little bit. Now, Lean very much supports imperative, but till maybe a year ago or so, you could not actually prove things. You did imperative programming if you just ran things, especially for meta programming. So that was the situation that we had these. But now there are two frameworks for verification of imperative programs in Lean, monadic. One is MVC Gen, and the other is from Ilya Sergey's group. So Ilya himself will be giving an introduction and demo of that, as well as Whale, which is a distributed computing verification framework built on top of that. So there's Loom, Velvet, Whale, 3 levels. We'll see demos of all of that. So that would be the third component. A fourth will be some little project demos. Okay, for people from the hackathon, people which Emergence had earlier, people who have been doing projects in summer. And if any of you are intermediate users, if you go beyond the core material and turn to the project part, then that too. Okay, so we will see these things. Okay, so I'm going to start with an introduction to Lean, as I said. So the self-guided part, let me get into in detail. We are going to have the following. So as I said, there is Lean for the curious mathematician and so on. But a lot of the material for Lean is mathematician oriented. This will be much more mixed. In particular, a lot of it will be programming oriented. Not against mathematics, but it's just that there isn't enough resource in any sense for programming or what we call meta programming in Lean. So there is, but still, if you are beginning in Lean, I would recommend using this excellent repository of Patrick Massot. So glimpses of Lean. So the way it is going to be, and the second repository we'll use, which is more programming oriented, is my collection. It's called LeanLang, and I will start with that. I'll give you a sense. It's less self-contained. So I'll be using that kind of not live coding because that takes too long as guided. It has exercises. You can work through the exercises and get some sense of Lean, but this will also illustrate things. One of the things that I, again, learned from experience is that it's not self-contained, and sort of the thing that glimpses of Lean and so on do is they become self-contained partly by restricting to a subset of Lean. They avoid many of the concepts, I mean, type class inference, even inductive types, various other such things. I don't want to do that. So we'll have daily Q&A sessions, which will be, I mean, I'll come with whoever is presenting it. Mostly it'll be me. We'll come with a plan, but you can ask questions and we'll go into many more details. So that's going to be every morning, 10 to 11, except tomorrow we'll have Ilya giving a guest version, and Wednesday onwards I'll be part of it. So that is the plan of these sessions. So then the bulk of the time will be labs, but those of us who know Lean, I'll point out, we'll be walking around and helping people as they work through the repository. Okay, so this is LeanLang. This is the repository. Is the font size big enough for people? I can zoom in if you need. Huh? One bigger? Okay. So this is just a header on top and so on. I get to a sense of what Lean is. And I want to give a full sense of what Lean is. So this is Visual Studio Code. This is the editor most commonly used with Lean. Installing Lean used to be a big pain. Even as recently as Lean for the curious mathematician, we had maybe of the 80 odd people, 4 or 5 who had trouble. But usually everybody would have trouble. I mean, some years ago. Now it has become a rare case. And of 4 or 5, I know only one genuine case. There were 2 or 3 who had very strange setups with their own laptops, and then they had trouble. So it's not really Lean's fault that they had trouble. But we come back to these things. Okay. So this is a repository, LeanLang, where I started at some point collecting all the demo code I had put in various things in one place. And then, so some interns, some of whom are here, were I told them try to learn from this, and then I got the useful feedback that I had to keep asking Gemini step by step or ChatGPT, whatever, what is happening here. So as a result, this has become more self-contained because I got Codex to do line by line annotation. So there is a line by line annotation in these things. So it should be reasonably self-contained. Of course, a good bit of it, some fraction of it, I'll go on right now in the Q&A sessions. We'll get to various concepts that are here. The other thing I've done is I've had a diagram where which guides and tells you this. For example, this file called smallest nat begins by telling you it's first file in tutorial proper, but there are some background files. Okay, so I'm going to start with this, but then I'm going to go to the background file because I realized when I was looking over things yesterday that, okay, the first file will give you a flavor of what is there in Lean, but if I keep going to second and third file, people will get incrementally more and more confused, okay, without certain background things being made clear. So I'm going to give this to give a flavor of what Lean is, okay. So here's the flavor. So the first flavor is you're usually working in Visual Studio Code. On the left-hand side is usually a file, and then you have on the right-hand side an info view, as it is called. Info view is actually a full browser. It shows you useful information as you go along. So Lean is a programming language, as I said. It's a programming language. I'll come back to it. From those who want to think from a programming language perspective, it's a programming language. Programming languages have type systems which are weaker or stronger. Probably the weakest is JavaScript, where basically anything goes. Python's a little better, but other things like Java and Rust are stronger. But thanks to discoveries from 50s, 60s, 70s, we know in principle we can have a type system that expresses all of mathematics. So it turns also into a language where you can prove things. And it is used a lot by mathematicians purely to prove things. Okay? This is a quick high-level view of it. So in some sense, it's a complete programming language. It's also a complete language in the sense of mathematics. But the third aspect of it, which I should say at the outset, and as you see, it will illustrate, is also has a lot of low-level engineering that has gone into it. People have taken trouble to handle error messages well, installation, various other things. This makes a huge amount of practical difference. And a lot of the success of Lean is because Leo Demura, creator of Lean, used to keep using the word paper cuts. I mean, if users have paper cuts, you're trying to use it and something is cutting you, then we have to fix it. So the attitude is there of the Lean developer that it's not that the users have to put up with it. I mean, it's a very pragmatic language in that sense. So I'm going to start with my first example. Okay, this is just, let's take a trivial thing. I'm looking at a list of natural numbers and I want to find the smallest element in the list. So here's the first Lean function. So just other comment about this interface for those not yet used to Lean. The thing about this is your programs are here, but it is also interactive. So Lean has both an interpreter and a compiler. The compiler doesn't compile all the way to machine code. It compiles to C, and then you use your system C compiler to compile all the way. So it is that, but the main work is compiling to C. Then you can use, well, Scala has this worksheet, which may be more similar, but people who have used, say, Mathematica may feel this familiar. People who have used Jupyter notebooks, they're not quite the same, but it's the feeling of that you can write code and you can interact with it. So those who have seen none of these, well, you'll see it here. But so here we are. So this namespace is just to avoid disambiguation. So let me take my first one. How do I define the smallest element of a list? So the way that is not ideal, but is often used in Lean is, well, the question you're faced with is what do you do with an empty list? Okay. So this version of it, which I call smallest I, is going to, first of all, if a list is a singleton, then that is the smallest element. Okay. Now this notation colon, if you have seen a functional language, you know, but it's otherwise the prepend notation. So Z's is a list of natural numbers. Y is a natural number. X is a natural number. So this is the list which is X and Y and then a whole bunch of other things. Z's may be empty. So this case is list with at least two elements. X is the first element, Y is the second element, Z is the third element. So here we do things recursively, which is I look at the smallest of the tail, that is Y and everything else. Okay. And then compare that with x. If the smallest of the tail is smaller, so the smallest of these two, the minimum of x and smallest I is the of the tail is the smallest. And then finally, there is the controversial case of the empty one. And in this case, I'm going to put 0. Okay. That's a junk value. This is often done in lean in practice. There's a question of which is better and which is not. Okay. I'm not going to get into that. That's often a pragmatic choice. What I want to, in this introduction to lean is to show you all the ways in which you can do this. Okay. So here you can evaluate the smallest element. There's a 1. There are a couple of 1s. So it finds the smallest element indeed as 1. It is not 0. If I evaluated it as these, if you are somewhat familiar with lean, you can try to guess why is this called smallest I. That's just a name. It's a name convention. Let me give 2 other versions of this before going to the one that we really want. Okay. So this one should be clear. Now I want to say, let me say something. Yeah, by the way, I'm going to take the policy that now as well as in any Q&A session, I'm going to be very leisurely. And my goal is not to cover any set. My goal is to, whatever I cover should be understandable. So please feel free to interrupt. Okay. Okay. So you may be unhappy that it's not showing any error message in this case. So I'm going to make a version of this. Okay. And that's going to be called def smallest just exclamation mark. Okay, now let's see if Copilot can guess it. Yes, exactly. So Copilot from the exclamation mark guessed what I mean to say. Okay, so let it put the string as well. Okay. No. Okay. This is a small variation of this. Okay, again, the same in these 2 cases, but here it panics. What does panic mean here? Panic means that if I evaluate this, yeah, no problem here. So now it gave a panic, which just meant that it threw a lot of errors and gave you an error. But if you evaluate, you'll see at the end of it, what lost. But if you evaluate here, it still gave the result 0. It should still give the result 0. Okay. It seems to not show it very. The panic is hiding things. Anyway, that's not an important aspect. Okay. So actually what happens, it still runs. It still gives the result 0, but it gives you an error message. I'm going to remove this. I'm going to comment out this. So this is a variant of the previous definition where it vanished. Okay. So now let me just say, we'll have much better variants later. One more now, and another one which is using what are called option types in another file, but that we'll get to by and by. Okay. So yeah, question. Why did I not have X and just Zs? Okay. It is because I wanted to explicitly say this matches things with at least 2 elements. You see, if you have X and Y and Zs, that matches cases with at least 2 elements. So if I had X and Zs, it would also match the 1 element case. Now you can argue, which is correct, that because the match with 1 element case came earlier, you don't need to be careful about this. But both when it comes to proving things or even just reading your code and maintaining it, this kind of discipline is useful, because when you read this, you know immediately it means 2 element cases. While on the other hand, if I still had 1 element case, X and Zs, you may read it and think that you want to have 1 element also works. Then you have to go back and read the previous case and say that matched. Okay. So the idea of, finally nothing is magical, but the idea of functional programming, and even more as you get to lean, is that you localize reasoning. Finally, you have to reason about correctness. But in an imperative language like Python or something, you may call a function and there's a list which is in the memory, and that function mutates the list. So some effect that happens somewhere far away may affect something here. So the idea of functional programming, and which is, I'll say, good software engineering anyway, but relevant here, is you localize. So this means that reading this match case only I can understand without reference to the other match cases. Hence, I chose to do this here. this logically true that because the other previous match came, it would be the same if I had this. And then what would happen is then I would have to say the tail is Z's. Okay. But what about the Z's being 0? Is then you'd have to think, is this reasoning correct? Oh, it is correct because if Z was empty, then the list would be of size 1. And because the list is of size 1, it would match the first case, etc., etc. So what I'm saying is that it makes things more error prone. It makes things slip by. Much better to say we match only these cases. But because you have raised this, thanks that I will say something that I forgot to say earlier. So the key point about functional programming, and I said Lean is not an exclusively functional language, is that the principal mode of looping, indeed the only mode, is recursion. And so recursion and pattern matching is what you'll use, where you would use a while and you would use an early return and elsewhere. Lean, of course, allows those as well. Not of course. We'll see examples of those later. So here's another example. Yeah. Any other questions? Yeah. No, not at all. So the first match happens. But I feel that having exclusive pattern matches is always good practice because it makes things easier to reason about, even when you want to prove and to prove things as well. Yeah. If it becomes just cumbersome to make them exclusive, then you don't. But in cases like this, where making things exclusive makes it more readable, then you certainly should make things exclusive. Yeah. We'll prove theorems. Okay. Just now, I'll give a different definition of smallest, and we'll prove theorems about it. So the thing about, yes, you can. No. Will panic is not a Lean's statement. But we can prove theorems about empty list and non-empty list in other ways. Yes, very much so. You'll see that as we go along. Okay. So far, so good. We have a couple of definitions. But here is what Lean really enables. Okay. So now what is this notion of smallest? Even before I expand the notion, I'm saying this is the smallest element of a non-empty list. So this is a function which takes two arguments. One of them is a list, and the second is a proof that the list is not empty. Okay. Now in Lean, this is the key feature about this dependent type theory and calculus of inductive constructions, that mathematical statements, this is not even true in mathematics normally. Mathematical statements are mathematical objects and programming objects just as much as functions are, just as much as numbers are. So in programming senses, you say what is a first class object. So functional languages where functions are first class, but a dependently typed language is where even propositions and proofs are first class objects. So I'm just passing an argument, which is that a list is non-empty. I'll go back to the more basic things and investigate them later. So these are the arguments, and here I define things. Now I have cases, okay, where I have in the first two definitions are exactly the same. What happened to the third definition? The third case never arises. Okay, now in the first definition, say for example, in the smallest panicking version, or where is my smallest I? Or in this case, if I remove the third case, I want to illustrate this key point. If I remove the third case, I get an error that there is a missing case. So Lean has an exhaustiveness checker, which, as you probably all know, Lean has an exhaustiveness checker and also a termination checker. We'll see the termination checker later. It has a loop, given a loop, I mean, with a bunch of patterns, it tries to prove automatically that these are all the patterns. And if it fails, it gives you an error. Similarly, that a function in a loop terminates, it tries to prove automatically. As most of you would know, you cannot prove, I mean, work of Church and Turing and Gödel and so on, say there is no algorithm to decide it. So it is a best effort case. And if it fails, then you can intervene and help it prove the rest of the cases don't vanish. But it has got smarter and smarter over time. And in cases like this one, it just notices because I said the list is non-empty. If I omit the empty list pattern, that pattern never arises. So without giving an error at all, it does these things. This kind of automation, I should mention, is just convenient for everybody. But if you're actually looking at programming or enterprise applications where you're doing program synthesis, it becomes crucial to have these kind of automations. Because if a user is working, that user will fill in extra details. But when you're doing program synthesis for whatever, right, business, enterprise, real world applications, it's important that the automation goes end to end without human intervention as far as possible. Of course, we all know it can't always happen. Okay, so this is our definition of smallest, and it has the unusual feature that the list is non-empty. But notice one more thing. I have to prove that the list is non-empty here, because smallest takes two arguments. Okay, one of them is that this list is non-empty. One of them is the list itself. So when I call it for the tail, I need to know that the list is non-empty. I mean, I give it a non-empty list and a proof that it is non-empty. Now, how do I prove it's non-empty? So if I go here, it tells me that I have to show that this list y:0 is non-empty. It's clearly non-empty, right? So Lean has automation, has had this level of automation for a long time. If I just say simplification, just simplify and prove this list is non-empty. So you don't have to keep proving by hand that lists are non-empty. Fine. So this is the case where we have it. Okay. So far so good. So we see some extra features of Lean that you can throw in hypothesis. Now, other languages like Haskell, Scala, and so on have types. Scala not native, have types called non-empty list and so on. But there you have to give specific types, and you have to somehow encode in a type what property you want. Here you can just put an arbitrary mathematical string, and then you have automation to help prove it. Okay, what automation and prove is and so on, I'll come to a little bit later here. So here we are going. So let me give examples here. So this is the first aspect. But the more interesting aspect is, well, we want to show that we got things logically correct. So what are the logical properties you want to prove about the smallest element of a list? One, it is in the list. And two, it's less than or equal to every element in the list. Okay. So here is the statement, smallest mem, which says that if I'm given a non-empty list, its smallest element is actually in the list. So if you're here, it says we are given a list which is non-empty, then the smallest element belongs to the list. I'll now give a slightly more verbose proof in 5 minutes. But right now, I want to advertise this fact that because, as I said, it's important if you're using it in enterprise applications, that Lean's automation more or less automatically does this. So fun induction is functional induction. It's a form of automation where something is defined by pattern matching or recursion. It automatically breaks it up into cases. I'll show you in detail. And grind is very powerful automation. For those who know, it's an SMT solver within Lean, plus many, many other things. So it's very powerful automation. So many proofs can be done just by saying grind. And others, you say we are going to use induction on the definition of smallest and grind. By the way, I forgot, I'll come to that. Forgot to say, while I've opened this thing here, Emergence hosts for you a live Lean server. It's called lean.emergence.ai, where LeanLang, it allows you to, so this is a fork of Lean's Fro itself made the server. We didn't make the server. What I did was added to it LeanLang as a project. So you can actually go with zero installation and explore LeanLang core. Okay, so after this, if things are working well, I'll post it on Zulip. There's a code where you want to learn programming in Lean. You, of course, hopefully have these things installed here. But if you or a friend doesn't have it installed or having technical issues, there is a live server which has all of these things online. Okay, so because this is too clever and hence a little obscure, let me do it in a more prosaic way. Okay, this is how you will prove things in Lean. So we want to know what there are many prosaic ways in which we do it. So smallest was defined by matching cases. A common idiom in Lean is that you prove things by matching exactly the same. Okay, so Lean's automation recognizes the cases are the cases. We did a pattern matching for lists in the definition. We'll pattern match for lists in the proof in the same. So as soon as I go to buy, okay, yeah, it is the same goal. It's just saying that if I have a list which is non-empty, smallest happens. As soon as I go here and I match, it is smart enough to note that the list has been replaced by the singleton X. And the hypothesis is saying the singleton X is not zero. Okay, as soon as I go here, this happens. Now, I don't know the definition. The next step
Okay, this is the prosaic proof. And you'll have to learn prosaic proofs because the automation doesn't take you all the way often. Okay, so here I'm unfolding smallest, which means expanding the definition of the smallest. And this unfold is smart enough to note that in this case, it's just reduced to showing x is these. And then you can use simp at this stage. Okay, so sorry, this looks obscure. Let me put it like this. So I can use simp. Simplification just finishes the proof. Okay, now simplification is an automation which automatically looks up lots of theorems. You may want to know which theorems were actually used. In that case, you can put simp question mark. This gives you a try this widget and click on this and you'll get simp only, or control dot if you prefer to use a keyboard, and you'll get simp only, and this is the proof. So this is the prosaic proof here. Okay, so without the magic of grind and without the magic of fun induction, more importantly. Okay, here we are. X, Y. So the second case now it knows that the hypothesis is X, Y, Zs are non-empty. Okay? And we simplify the smallest using the definition of smallest. Now we are proving by induction. So have introduces a new result. Okay, so have is defining something. So let and have are two statements that allow you to define something new. So I'm defining induction hypothesis as the same theorem called by a simpler one. Lean now notice that this actually terminates where you can't, it really is a simpler one. We'll get to termination and so on, maybe in more examples here in Q&A. I don't want to go to that. So now it has got a little bit complicated, but it has the induction hypothesis. And then I say grind. Traditionally, you would work a little more, but grind just says do it off. So this is actually the same proof done here. Okay, so this is somewhere in between the two. These are again the summer interns I should thank. Yeah. Okay, so generally speaking, so simp is a simplifier. So there are a bunch of rules that are marked simplification rules. You can also tell simp use these particular theorems. It uses them as simplification rules, but it has no backtracking and it only keeps simplifying inductively. It looks at all simplification rules, sees if anything matches in a fancy sense, fill in arguments, etc., what is called unification, and monotonically keeps simplifying things. And it is also not necessarily a finishing tactic. It may not solve your problem. It may simplify it and give you a new goal. Indeed, that's what we did when I did simp smallest. So here, when I use simp smallest, I tell it to use whatever. In fact, it is strongly advised in Lean that I do this, simp question mark smallest, and then it will do simp only, smallest list dot memcons, etc. So it used this theorem and it simplified it. Okay. One of the things is, though, if it tries the simplification rules in order of priority, and if one of them works, it works. Now, one simplification rule might break the other one because it changes the nature so that it would have previously fit the other one. There is no backtracking. There is no search. It's monotonic. And if your simplification loops cause you to go in a loop, it just hangs. You're supposed to make sure it's non-confluent. Okay. So it's a powerful form of automation, but only this far. Sometimes simp works though where grind doesn't, and in particular as a non-finishing tactic, you can't use it. Grind, on the other hand, is much more powerful automation. It backtracks. It uses a way where it keeps accumulating deductions, working them out. It uses a sort of scratch pad and deduces things. It has many, many solvers plugged into it, including a full linear programming solver. It uses SMT solver. It's a SAT solver. Various things aware of Lean. It does simplifications. It does various other things. You can also denote lemma as grind, in which case grind uses it. Okay, so grind is much more powerful, complex automation, which is extensible and so on. So that's the difference here. So here we see almost straight away. So in this particular case, this is, yeah, question somebody. So simp or simp only can be followed by square brackets with the list of names of theorems. Because I've changed from simp to simp only. Okay. So simp, so there are two kinds of theorems that are used both in simp and grind. Thanks for the question. It was a very important question. One are those that have the attribute simp associated to them. That is, when you state the theorem or somewhere along the way, you say this is a simplification rule, simp use it. So any result that is in scope and which has in the scope this attribute that use it in simp is used. So list.memcons, and in fact, if I go here, so great thing about Lean is it's written in Lean, so you can just follow by control clicking. You see this has the attribute which is simp and grind equal to. That tells you use it in simp, also use it in grind if you are proving an equality. So because this had the simp attribute, it was used automatically. On the other hand, I don't want to put the simp attribute to smallest, which is a definition, because it might mess things up. As I said, expanding with simp can be destructive at times. So when I did not have simp only, I only told it use smallest and use whatever lemmas you know in simp. Simp only says forget what lemmas are marked with attribute. Use only those that come in brackets and certain other rule-based simplification. So simp only with no parameters also works, but it doesn't use any theorems. It uses other kinds of automation. So when I switched to simp from simp to simp only, it did this. General point as you learn Lean is if it is non-terminal simp, it is strongly recommended that you put a simp question mark and switch from switch to simp only. This is because as the mathlib keeps getting updated, new lemmas may be marked as simp and they will get used. Simp's own code can change. So all sorts of things can cause simp to break if it's not terminal. So especially non-terminal simps, it is always recommended that you put a simp question mark and switch it over. This is also recommended for terminal simp, but much less seriously. So MATLAB, they will reject it if it has a non-terminal simp. So it is by default used left to right, but you can put a left arrow with simp and then it's used right to left. So there are tactics called simp and rewrite. They can be used in either directions. Yeah. Yeah. So if you go through glimpses of Lean later in the lab sessions, you'll see all these explained you'll see rewrite used. Yes. So it's left to right by default. You can override and tell it use this particular thing right to left. And if it's not an equality or an if and only if it's a definition, also it'll expand it. So certain things it'll just give you an error. Simp is meaningless, but yeah. Simp smallest is simplify using the smallest definition. That's what the meaning of simp smallest is. Simp only, this says simplify using only smallest list.memcons inf equal left. Okay. Now you can probably guess what this means. List.memcons, cons of a list is one list appended to the other. Cons is adding a list to the other. This result which you use tells you something is a member of X colon B colon L if and only if it's either equal to the first one or it's in the second one. These are all basic MATLAB theorems. Sometimes they're in Lean's core itself or STD or batteries. So in something which will be in your things here. Yeah. So for this program, it's fine. Okay. But if I use simp, what it does is it looks at all the available lemmas and does them in a particular sequence. Now MATLAB is updated all the time, and a new stable release comes every month. Now, what happens if a new lemma is proved, which simp can use, that gets higher priority and is annotated simp? Then the behavior of simp has changed because it's using this new simp rule. So since adding simp rules is always a legal change in MATLAB, that can break simp. It will not break simp only, because simp only tells you exactly what are to be used. So simp is not recommended. There is a second more minor reason, but the major reason is because additional simp lemmas can break simp. But additional simp lemmas will not break simp only. The other minor reason is that if this lemma goes away, it gets replaced by some other name or something else. It's easier to debug. You see, this lemma has gone away and you can find in documentation or release notes what happened to it. Or is no longer a simp lemma, for example, then somebody will tell you what happened. So that's another minor reason. Simp lemma may go away because people may find a more general lemma is what you should have simp for instead. Or you may have that a simp lemma is decomposing and blocking the use of other simp lemmas. So there are various reasons why code is always refactored like this. Yeah, so it can go away for these reasons. Yeah. Yes, but it's a bit complex. You can't completely control it. You can give them priorities, but at some level, because of optimization and so on, you don't have full control over the systems. If you're using the same version of all your dependencies, yes. If your tool chain is upgraded, you add an additional library, you remove a library, no longer the case. That's the point here. It is maintainability because you don't want things to be too dependent on these things. Yeah. If ever you have used Java or something, which I had to because of Scala, you know, because of what's called dependency injection, how your brain can be utterly fried because something changed somewhere else can mess up everything. I mean, and you don't even know because something somewhere had that inject. So yeah. So as I said, you want to localize the effect as much as possible. In that spirit, you should be using SIMP only. Yeah. Any other questions? Okay. So now this was an intermediate example. This time I'm going to use the fancy functional induction and show you what happened. In this case, you got two cases. It's called X dagger because X is already used, I think. And anyway, dagger means it's an internally generated variable. It's not directly accessible. Lean does a lot of shadowing to allow avoid name collisions for you. And a second case is more complicated, but you notice the important point here. Let me send this here. This tactic was smart enough to generate that induction hypothesis, which I did manually for you. Fun induction or even the induction tactic, fun induction on smallest, actually called smallest on the previous case and put that in the info view. Oh, I haven't explained the info view. Maybe this is a good time to explain. What do you see on the right-hand side? What you see on the right-hand side is all that is in the context. Two natural numbers called X and Y, a list called Zs, okay, with always daggers, a hypothesis called H dagger, which says X, Y, Z is non-empty, and another hypothesis, the induction hypothesis, which says smallest of these belongs to the list, which is the smallest. And what you see after that turnstile symbol, the T which is lying down on its side, this is standard notation from logic, is what you have to prove, your goal. So this is the set of things that you have seen here. Yeah, so this is the way in which these things go. So your info view, what you are typing are tactics. What they do is try to modify the info view. Okay, now they usually the goal is they make progress. Sometimes they regress as well. I mean, in a full course, of course, I give examples of regression, but with the short time, I won't get into those examples of regression. So let's go ahead. So in this case, and here it gave you all this, but this was part of SIMP and grinds thing. I don't think SIMP is strong enough at this case. SIMP only simplified it, but did not close it. But grind is just stronger. It closes it for you. So this is a sort of expanded version. So here illustrating the first case, base case, which was simple, SIMP did the job. The slightly more complicated case, we had to use the newer automation. Okay, so this was one. And smallest LE all, what I did is literally copy pasted and changed that statement because this also can be proved by fun induction and grind. So you change the statement, doesn't matter. Fundamentally, the proof is the same. We proceed by induction. Rest is trivial. Rest is left as an exercise to the reader. Okay, so you can think of grind as leaving as an exercise to the reader. I did this just to illustrate that first case SIMP was good enough. You don't need grind. Yeah. But you can just use grind. And so, oh, by the way, so that also brings back to the point, what is this semicolon with triangle? Which I had, no, in my earlier proof. No, it's here as well. Sorry, here it is. So what is this? This says use this thing which is inside left than and greater than sign, you put a semicolon, means use for all cases. So when you do fun induction, it splits into more than one case. Okay, you have more than one goal, as it says technically. This semicolon means all goals. In all cases, use grind. So indeed, I used grind for all the cases. Because in this case, when I want to automate, grind is good enough for everything. SIMP isn't good enough for everything. So The third will be the strongest reason. Okay, so one is simp works where grind doesn't. You can say we ought to simply strengthen grind, and I'm sure people at LeanFro grind. By the way, Leo Demora, the creator of Lean himself, is working on it. So it's the high priority thing. So that's the main priority thing. So hopefully grind will get stronger. It's got stronger and stronger in the last few months, where it will cover the simp cases. So this may be a passing phase. Second reason, which is the weakest, is maybe simp is historically there from the start of Lean. Grind came only a few months ago. But the third reason, which is why you should always have simp, is you notice we use simp smallest that was non-terminating. Grind is a terminating tactic. It either works or it fails. But simp can be used for partial simplification, and then you continue working from then on. When I said simp smallest, my goals got changed after certain simplification. And then I did something else to complete the goal. So that is the fundamental reason why simp will always work. It's a simplification rule, which is also used for partial simplification and not necessarily in the termination case. Now, Ilias Group has a version of non-terminal grind as well. But still, simp will remain. As a non-terminal tactic, though, simp is going to be an important part of Lean forever. I mean, it's not going to go away. Yeah. As a terminal tactic, it is possible that at some stage, grind will just work where simp works every time and it might become redundant. So now, when I call this, there's a little bit of a nuisance. I cannot call smallest without proving this list is non-empty. Right? I have to give smallest two arguments, a list and it's non-empty. Fortunately, automation, which is by simp, does these things. Okay, now you might say, this is a pain. Why do you want to force us every time to keep typing stem? Okay, so this is where we get a peek into a nice feature of Lean. It's actually a fantastic feature of Lean in its full strength, which is its meta-programming capabilities, which is a way to extend its own syntax and introduce new syntax. There are much more sophisticated ways, even including this repository has a lot of sophisticated metaprogramming things, which we will not, I mean, those of you who are intermediate can turn to those in your exercises and ask questions in Q&A and the labs, but otherwise we won't, you probably won't get to that. But the great thing about Lean and any well-defined language is you can do easy things in an easy way and you have to do sophisticated things in a sophisticated way. So this is something quite easy, right? I just want to put by simp automatically. So the easy way is I just make what's called a macro. Smallest percent, it's a bit of a convention in Lean. Smallest percent is just the name. The percent has no special meaning here, but the convention says that if I'm going to give a term, an object, I should put a percent after these things. So smallest percent is just takes the term L and replaces it by smallest and by sim. And now you see if I do smallest percent, I'm done. So there is no need to evaluate things. So this finishes the first file. I'll go back to the very basic file. And then because I want to show the power of Lean, since this is the sort of introductory session, I will jump to a more advanced example, but that will be without too many details. So any questions? So my plan for this first session is just in the next 15 minutes, we'll go back to even more basic stuff and then come back in 20 minutes to an example which will sort of illustrate that these are not just toys, they actually run. Okay. So any questions before that? Yeah. I mean, there are plenty of restrictions. Of course, it can't be unrestricted. For example, it cannot have a space. And certain Unicode characters are allowed, certain others are not allowed. In fact, on Lean Zulip, which is where you should go for help, there are often discussions because people speaking, for example, some Slavic languages really want to use some character, it's not allowed. But percent, question mark, and even parenthesis are allowed as part of identifiers in Lean. So quite a few things which are not allowed in most other languages will be allowed in Lean. This is, yeah. So exactly what it is, I can't tell you, other than the most obvious case that you can't have a space. And yeah. Evaluation is execution. Simp is required because if you look at the signature of the smallest function, it has two arguments, a list and a proof that the list is not empty. So I have to give it a proof that the list is not empty. So the second argument here, if I go here, is that this particular list is not empty. And how do I prove that the list is non-empty? I'll use sim. And there are many other ways in which I could prove it. But the easiest way is to use grind, for example, will also work here. You can also prove by hand. Okay, so this is the question. Yeah,
It's an argument.
it's an argument and generated by automation. So this is kind of the balance here that you can ask for a lot, you can ask for types, but they're often inferred. You can ask for proofs, but automation usually does it. So otherwise you have the sort of annoying trade-off that you either are stricter and stricter, which will reduce your errors but increase your work. So the only way you can really make progress, sort of Pareto progress on both axes, is to be able to have good enough automation that, so for example, if you're using smallest percent, that means there is no extra effort over using a completely unproved function. Okay. But for example, let me give you an example here. Hash eval, if I do smallest percent of this, you'll see an error. This error message is slightly obscure. It says unsolved goal false, but you can guess what it is. It tried using simp to prove that the empty list was non-empty. It simplified that to saying empty list is not empty is equivalent to the logical goal false. And you'd be quite alarmed if it managed to prove the logical goal false. It failed to prove the logical goal false, which is the error message here. So you have got your safety if you're using smallest percent by getting an error if you try to use it where it should not be used. But where it should be used, it often works. Of course, this is not magic. It may be that a list is really non-empty, but it's not obvious it's non-empty, and simp will not do the trick for you. And so we are here. Yeah. Your question is that here it's a literal, so it's especially easy. But if you notice over here, if I look at, in many cases, I use simp or grind. That was in another example, which was the example I had in mind. Okay, I'll show you here. So for example, we already used it for a slightly non-trivial case. If you go back here, it used it to say anything of the form y colon colon z's is non-empty. So that's not a literal. Okay, but this is a very important question because with a literal, you can say that nothing special. Even Python could tell you that literal is non-empty. You could just have an assert. There's no real proving here, but this is actual proving. Okay, and if you go to the exercise, you'll see another example. This is a slightly hard exercise. If you know some proving, you could do it, but it's the one I could think of. There's an even harder one that I had first put. Okay, so this is saying, so filter of a list is given any property, it throws away anything which is non-empty. Okay, so this is the theorem that if L is a list and this is a Boolean function, it says true or false for every natural number, and the filtered list is non-empty. Okay, only then smallest of the filtered list makes sense. Then the smallest is less than the smallest of the filtered list. Okay, but what do I mean by smallest here? Now, if you look at the right-hand side of this, the smallest is called for the filtered list with a proof H, which is the proof that the filtered list is non-empty. But what about the right-hand side? Okay, it is smallest L, and I have to give a proof that the original list is non-empty. Of course, after filtering, if a list is non-empty, the original list must be non-empty. But this is a proof. I mean, this is not a triviality. But I can just say by grind, and grind will do it for you. Grind, note this is non-trivial. Grind has to notice that the hypothesis contains a fact that list.filter PL is non-empty. It also has to pick up the theorem that if a list, after filtering a list, if it's non-empty, the original one is non-empty. And use those two to put together that this hypothesis makes sense. So yes, so the automation actually proves things beyond just literals. But this is a very important question. The important point is that if it was just literals, the proving power is not really there. I mean, it's there, but it's a sort of fancy, almost marketing. I mean, it's not a, yeah. What is the context of the grind? Yes. So the context of the grind is all hypothesis in context. In addition to that, anything annotated by grind. And you can also put square brackets and explicitly tell it to use things. So its scope includes things that are, but in particular here it is, I mean, your question is, was motivated by this H. Yes. So anything that is in the goal state, which is in the current local context, as it is called, is in the scope of grind, in addition to grind lemmas and so on. There is also a version called grind plus locals, which will use everything that is in the present file as better than these. Okay. Any other questions? Okay. Thank you for the question. When one gets used to it, one forgets that certain things look extremely obscure. So where is my, it's down. Okay, here it is. What is this backtick? This goes back to the second oldest programming language, namely Lisp. And these are what are called quasi quotes. Okay. So the notation is not just a backtick. Backtick parenthesis, close parenthesis. This whole thing is what is called a quasi quote, which means that anything inside that is syntax. So it is not a term to be evaluated. It is a syntax to be specified. Now the smallest, it noticed, is just the definition smallest. Because it was in scope, it treated it as smallest. If you give a non-existing number, it actually puts a dagger on it, etc. But since smallest was a name in scope, it left it here. $L means I'm referring to L. So L colon term means L is not a term, it's a syntax for term. And $L is interpolation. Many languages have string interpolation, you would have seen in another language. This is a fancier version of string interpolation. It is syntax interpolation, but it more or less behaves. So many languages will have dollar, or they'll have braces, or some way or the other of interpolating strings. So this is interpolating syntax. The rest of it is just literal valid syntax, which it has checked and given it here. So anything inside backticks and this, you can even reverse this when you can match syntax and use quasi-quotes. That becomes essential when you're using more sophisticated metaprogramming. But in this case, it was this. Yeah. Yes, there is automatic escaping because it noticed smallest was in scope. It kept it as smallest. Otherwise, it would put a dagger after the smallest. If I used the largest or something here, it would just put a dagger after this. Lean is very careful about hygiene, but fortunately, it gives you lots of helpers at metaprogramming level to use its hygiene. I'm not sure if I want to even go to basic things. I think I should go to at least the first of them. Okay, so okay, the plan for the rest of this, because I'm stopping at 11. As I said, after that, feel free to keep asking me questions. And Wednesday, Thursday, Friday morning, I will again set up for an hour here and answer all the questions. By then, you'll all have been working through things and asking questions. But in the lab also, you can just ask questions. You don't have to work on exercises. And not just me. When we'll start the lab, I'll point out who are the others who know Lean, whom you can flag down and ask questions to. If some of you know Lean, you can volunteer to answer questions, meaning some of you know Lean and I don't know you know Lean. Also, you can volunteer to answer questions. Okay, so I'll just go. So my plan for the rest of this is that I'm going to, in 5 minutes, such 10 minutes, say some very basic things about Lean. And then I will go to quick sort as an example of an actual algorithm that is used in production rather than something toy like smallest. I'll give some quick overview of that running in Lean. So the foundations of Lean, which we can go into depth later, but just quick overviews. Everything basically in Lean is a term. So that means numbers are terms, functions are terms, lists are terms, data structures are terms, but also propositions are terms, proofs are terms, and terms have types. And types are themselves also terms. So everything is a term. Terms have types. Types are unique. We can form expressions using terms and types. These expressions may or may not be valid. And we can make two judgments about the expressions. One is you can make the judgment that the term A has type alpha. And also term A and B are equal by definition, or judgmentally or definitionally equal. I should emphasize, just like you would say in any given human context, absence of evidence is not evidence of absence. Similarly, absence of judgment is not judgment of absence. That you fail to judge term A has type B, or term A and type B are equal to each other, or term A and term B are equal to each other, does not mean they are not equal or it doesn't have the type. For example, Lean will be able to judge that 1 plus 1 is 2. It will not be able to judge that sine squared theta plus cos squared theta is 1, even for a concrete value of theta, even though that is true. Okay. So what you do is the judgments are algorithmic, they are fast, they're done at the kernel level. So this is the high level of view of Lean. When you work through, you already saw eval. There are two basic commands you can use working. One is called check and one is called eval. Okay, there are many others. This hash, by the way, is purely convention. You can introduce commands called anything else, but if you introduce a new command, which is not a core part of Lean, these are pretty core parts of Lean, but anything beyond the definition, theorem, lemma, and so on, you usually begin it with a hash. This is just naming convention. Hash is legal part of every identifier. So we can evaluate things. For instance, we can evaluate 2 plus 3 is 5. When you evaluate things, it simplifies, it reduces. I shouldn't use the word simplify. Technically, reduction is more restricted than simplification. It reduces and then gives you the result. Eval tells you this. Check tells you the type of a thing. So check 2 plus 3 tells you 2 plus 3 is a natural number. Okay. It also tells you, I'm going to close all messages. Let's focus on the message in the context. I'm sorry. I closed this as well. Okay. The message in the context is 2 plus 3 is a natural number. And hello is a string. Natural numbers and strings are also defined in Lean as what are called inductive types, but I don't have really time to go into that. Okay. Okay. So check to, now you could say, you could specify explicitly 2 should be regarded as an integer. This is the notation, in which case when I add 3, it becomes an integer. 2 plus 3 becomes an integer. Yes, you can override plus. But if you add a string to a natural number, this is illegal and it will give you an error. You can, that's the type class story. You can introduce your own notion of addition. Those are more advanced examples, which I won't get to today, but maybe on a future day, one of us will get through that. Yes, even from that, it deduces that 2 plus 3 is a natural. That happens, that's type inference. That happens when we define functions. We'll see that. Okay. So we'll check natural number. So natural number also is a term, as I said, types are term. What's its type? Its type is this thing called type, capital T by P. Type is what is called a universe. It's a type whose terms of that type are themselves types. Okay. Integer is also a type. And what about type? Its type is called type 1. To avoid paradoxes, you cannot have type being itself. So type becomes type 1, type becomes type 2, etc. If you are interested in foundations, let me remark in passing, this 1 is not the natural number 1. It is what is called the universe level 1. There's a duplicate copy of natural numbers called universe levels, which is more foundational in Lean. Natural numbers themselves are an inductive type. Okay. Okay, so far I dealt with literals. I can define things. I can define 2 as a natural numbers. Okay, this is definition of 2 is a natural number. I can define 5. And now I see they are natural numbers. And I can also evaluate. Now let's go a little bit ahead. Slightly more sophisticated are function types. Okay, so function types, given a type and another type, I can define functions from one type to the other. For example, natural numbers to natural numbers. And let's define a function from natural numbers to natural numbers. Okay. Cube takes a natural number as output and gives n star n star. It's obvious what this definition means. And if I check cube, I get the type. Okay. Here it gives it this way. But this is actually the type up there. You'll see the goal nat to nat. This has type nat to nat. There's a lot of things which are made for readability. So it's giving you the other form because it assumes more people are concerned with working with Lean rather than looking at foundations. If you're really interested in foundations, actually the language you should be using is Agda, which is a beautiful language, very much focused on foundations and where many more, with much less automation, which makes things very transparent. And it's developed at Chalmers, where Thierry Coquand and co are. Thierry Coquand is the person who developed the foundations of Lean as well. So they have the same foundations. Lean is a pragmatic language. It's not foundation focused. Agda, AGDA.
So Agda, Coq, or Hawk as it's now called, Lean, all these use calculus of inductive constructions, which builds on Martin-Löf type theory, which all in turn builds on other things and so on. But the big advances are due to Per Martin-Löf, who's in Stockholm, and Thierry Coquand, who's at Chalmers. These are the people who are the big advances. Yeah. So Agda is developed in Chalmers by the group involved in that. The founder himself. So yeah, so it is closer to foundations. Now we can evaluate cube of 3, for example, and you get 27, not surprising. If I eval cube, I get some error because evaluating a function doesn't make sense. Okay, so this is what is called type classes. I don't have time to go into that, but it's in the repository. You'll see it. We can get back to it at question times. But it says I don't know how to represent or write as a string a function. Of course, we don't know how to write a function things. Okay, but you can print, and that just prints the definition. It's not printing the value. It's just printing the definition. Print only works for value. If you say print cube 3, it will say this is nonsense. Okay, so you can either print a definition or you can evaluate something which has a way of representing it. Okay, so just the other way of defining it. So here we defined it like with more natural languages, but you can defining it using the maps to notation. Okay, so cube is a function which will take n and map it to n star n star n. Again, this should be completely readable. You can use equal to an arrow instead of maps to. That was the original, that's actually the more built-in notation, as is used in many programming languages. Maps to is used in mathematics, of course. So this is something which will map n to n star n. Fun keyword tells you it's a function. You can also use the lambda. Correct. Thanks for the questions. So you type maps to, maps to, and it types maps to. But if you wondered how to type it, what you do is go and hover on this symbol and it will say types using this or this or this or this. Actually, there are 4 ways to do. So if you see in the code something and you don't know how to type it, hover on it and it will always tell you in its documentation string how to type it. These are the kind of low-level details which are absolutely critical to adapt Lean being widely adopted. You don't have to go and search on a third-party website or have a cheat sheet in front of you. I do keep forgetting how to type French brackets, for example, and then I have to go and find some code which has French bracket and hover on it, which is inefficient. But most things I remember how to type, which I ever need to type. Yeah, there are cheat sheets available here and there, but if you see things, just hover on them and they will tell you how to type it. Okay, now interestingly, here I defined it, but these are literals in themselves. Literals is something just given as an expression. Function n goes to n to the n plus 2. So I can simply check it. And it tells me this is the function going to n plus 2, which goes from natural numbers to natural numbers. Notice I actually did not tell it that it goes from natural numbers to natural numbers. It saw the 2, it saw the addition, and inferred that these must be natural numbers. Okay, but if I want to, I might say that actually I wanted to go from int to int. I could put this and now it goes from int to int. So I could specify the type and do this also. Okay, so there is type inference is an important part of automation, which means you can have extremely strict typings without extremely high headache that comes from doing it. So this is the thing. I mean, again, I've fortunately never programmed in a language which doesn't have type inference. But when I use Scala, I had to use Java libraries enough to know how horrible life can be if you have strongly typed languages without type inference. People from software will probably have this awful experience of using these languages. Actually, there, instead of type inference, you have your tools which will generate the code for you. So it's not that bad. Yeah. So this itself is an expression. Expression is what you see. It's a piece of syntax. Term is what it means internally. So expressions and terms are the same thing. Expressions are expressions for terms. Expressions are how you write a term. Like even in mathematics or anywhere, you write something on the board, right? There's a difference between what is represented with what you write on the board and the actual chalk there. So you think of expression as the actual chalk on the board and the term as what it represents. Except that expressions themselves are syntax, they are part of Lean.
So there are kernel expressions that represent terms. Yeah. So you can think of terms at one level and expressions as in both syntax and kernel expressions are there are different levels of internal representations. Yeah. So I'm using the things interchangeably because they're different levels of abstractions of the same thing. If you really are working at foundations or meta programming, you have to be careful whether you're doing kernel expressions or syntax or terms or something. But yes, for at this level, you can think of them as interchangeable. So here you not only can you do it, I can evaluate this function acting on 5. Okay. One thing to warn if you're not used to functional languages, it's kind of the opposite. In most languages, you put brackets around functional arguments. Here you don't have to. You can or you need not. Okay. But I do put bracket along this to tell you the precedence that this part is a function and it's evaluated on this. Yeah. Why am I, this is, you could try to have notation which n maps to, in ordinary mathematics, you would just write n maps to n plus 2, but this will make Lean's compiler or parser's job extremely hard. So the fun keyword is needed. Line 94 to tell you this is a function which takes n maps to n star n star n. To a human reader, you do not need fun. If I remove the fun, this would still, you would be able to read what it means. However, Lean is ultimately a programming language. The question you can ask is, why is fun not optional in this case? It's because that would make the job of Lean's compiler, parser, interpreter much harder if you allowed the maps to notation. Huh? You're correct. So it could have been implicit that you could drop the fun. This is something Lean's. So the fact that I have to write fun is because that's Lean's syntax. Def tells you that we are defining something called cube. It need not be a function. For example, I define 2 is 2, right? So def is I'm defining a term. It need not be a function. And this is telling you this is what you call a function literal. This is telling you this is an expression representing a function. That's why I wrote it here. That was what I was kind of answering. So the thing is that maps to a human reader will tell you automatically it should be a function. In principle, you could say Lean could have tried to allow you to emit function, but I would safely trust Leo de Mora's judgment here that the extra effort that will improve ergonomics of the reader, but the extra effort and possible ambiguity at the level of Lean's core, its compiler, its meta programming, etc., is not worth it. Forcing people to type fun is to make all the other layers easier is worth it. Yeah. Okay. So, so this was, okay. So let me just say curried functions is briefly, I'm going to say this once and then I'm going to jump to quicksort. Okay, because I would just want to show what serious programs can be done before winding up. Yeah, I might go on 2-3 minutes over time. I don't want to go long over time because you can always ask questions. Okay. So one of the things currying, which goes back to Curry, of course, Haskell Curry is his name. So Haskell is named after him, as is a language called Curry, and there's a language with name after his middle name as well. But anyway, so he's a logician. So he observed the following, that a function of 2 variables can be thought of as a function from one variable to a function from the second to the third. So if you think of sum of squares, you can think that given 3, it gives you a function from the second argument to the third argument. So you think of a function from natural numbers to natural numbers to natural numbers, which given 3 will give you a function from natural numbers to natural numbers. Given a natural number, it's 3 squared plus whatever else, and this way as well. Okay. So I could write this example in a more verbose way. Yeah. So it could also be written this way. Okay. So for paucity of time, I will not go into these things in detail. I would have liked to show propositions and proofs. As I said, we'll have time further on. Yeah. Let me, jump to real. Any questions, or I jump to a sort of real example? By the way, there are many ergonomic features of VS Code also important. Control P lets you jump to other file. Okay. So quicksort algorithm, it's working from here. Probably everyone knows quicksort. Just to quickly remind you, it's a way of sorting a list. Okay, it's a way of sorting a list where you start with pick a random element, call that the pivot. Okay, but you could pick the first element as pivot, which is what I'm going to do here. Okay, take the rest of the list, split it into those that are before the pivot and after the pivot, and then run the list with, then sort the rest, and then put the part that is before the pivot, and everything else. So we pick the first element. Okay, compiled it. We are ready to go. So if the list is empty, return empty list. Otherwise, pivot is the first element. Smaller is the list of elements that are smaller, and larger is the list of elements that are larger. And now I'm going to do it in generality. I'm going to take any type with a total order on it or linear order on it. And when I looked at smallest NAT, okay, this LeanLang builds up to this case. Smallest NAT I just took to natural numbers, but you can sort anything which has a linear order on it. Okay, and I'm defining smaller as those elements we already saw filter, which are less than or equal to pivot, and larger as elements which are greater than the pivot. I tell grind and simp, you can both use this. Okay, grind and simp are the annotations that are used, which use it here. Okay, so there is a naive way in which I can define quicksort. Namely, empty list is empty, and if I take pivot and L, okay, then I can just take the smaller and larger and put the pivot in between. What's wrong with this? If I just wrote this as a def, I'll get an error. The error is Lean failed to show this terminates. So the thing with Lean is by default, if you say def and the function is recursive, it tries to prove termination, just as it tries to prove exhaustion of pattern matching. And if it fails, it gives you an error. But in the spirit of Lean, Lean is a very pragmatic language, I can just say partial def. The notion of partial functions goes back to Church in the 1930s. So partial function means it may not terminate for some values. There are many subtleties here, but the thing is, it's pragmatic. It's your choice. You prove things are correct or you don't prove they're correct. It's up to you. And if you don't, then you want to shoot yourself in your foot, be my guest. Or if you think it's not worth the effort, be my guest. Okay. But this quicksort is the same thing, except I told it terminates by the length getting shorter. Okay, so now let's look at this definition. It matches the empty list, it's empty list. And if it's pivot and L, it takes quicksort smaller pivot L, then the pivot, and quicksort of larger pivot L. Is part of Lean. It's a core part of Lean. So to prove termination, so if it cannot prove termination automatically, you can help it at different levels. I'm showing you the most basic level of helping here, which is tell it what function decreases with some partial order or the other. It could be a pair and it's smart enough to use lexicographic ordering. It's smart enough to use the arguments themselves if one of them is a natural number. It automatically tries various things. But here I tell it the length decreases, hence it terminates. So in any recursive call, the length is smaller. Now, how do you know the length is smaller here? I actually did a little macro in the previous file to tell it use grind for this. But in addition to its default termination tactic, so that simplified things. But termination is a topic in itself. What I wanted to show is that it terminates. By the way, there's a common enough error. You might forget to delete the pivot from one of them. So it's quite not trivial. They're not uncommon that you will make an infinitely terminating thing in this case. So this is a level of protection. Okay. But what else do you do? Well, we can prove obvious theorems, and it's kind of an idiom that you prove the special cases separately. I will jump to that. And these are intermediate lemma. And let me just show the main theorem, since in this portion, I'm simply trying to show things rather than do them in detail. We can prove the two main properties of the sorting algorithm. One, that you're a member of the sorted list, if and only if you're the member of the original list. And nicely enough, this is easy enough. I just do the functional induction and grind. So Lean's automation. I've done quicksort over years. At the first time I did it, I had to work a fair amount. So the automation has become stronger and stronger. Now functional induction and grind is enough to say you can just prove quicksort here. So I think it's quite impressive that production quality sorting algorithm can be proved basically completely by automation here. So this is the first property you want to prove. Now, the other thing you want to prove is that it is sorted. So termination by uses something called termination tactic. And termination tactic is some complicated automation. And if termination tactic includes something called termination trivial, and I wrote a macro saying that it has a default thing which it calls termination trivial. I told it use grind as termination trivial. That's in another file. So I sort of souped up its automation, telling it also use grind. Without that, I would have to do a little more work, okay, of a nature that I don't want to get bogged down. So lots of termination happened nicely and quickly because of these things. Okay. So here is the functional induction and grind dustings. So I used to have to work much harder. But the other thing I wanted to prove is that, well, you could get the same members by just returning the list itself, right? The list is sorted. So what do I mean by sorted list? Well, I have a type called sorted defined in another file. Okay. And this is what is called an inductive type, but you can think of this as axiomatizing the notion of being sorted. So this part is more not really demo, just a more a spectator kind of thing. So I axiomatize the notion of sorted by saying that the empty list is sorted, a singleton is sorted, and if I have a list with at least two elements, so I have X, Y, and L, what was called Z's there. This is sorted if X is less than or equal to Y. And so if the tail is sorted, that is the second element onwards is sorted, and the first element is less than or equal to second is sorted. Okay. So with this kind of axiomatization, we actually prove, I'll come back to this axiomatization in a moment. We prove that quicksort is sorted. Again, this needed a lemma which took a little bit of work, which is that sorted is sandwich. If I took a list which was sorted, L1, L2, both of them are sorted. They're bounded by two numbers. And I put a number there, both one part is less than or equal to X, another part is greater than or equal to X, every element. Then I take the sequence, then the result is sorted. Okay, this takes a little bit of work. I won't go into these details. We can discuss in the many times over the 5 days. Okay, but given this, it comes to that. Okay, so the last two things in this session, so that I'll end on time, are the following two. What if my definition was wrong? How do I trust my definition of sorted? It seems a bit subtle. Maybe I get it wrong. How would I be more sure that I was correct? Well, I'll give a second definition. I will call that monotone. Okay. And this monotone is a slightly more readable definition. It says that if I take a list and I take for all I and j, if I is less than j and j is less than length. Okay, so I and j are indices and they both have to be within the range of the list, otherwise it's illegal. And I is less than j, then the value of L at I is less than or equal to value of L at j. So this is another definition of being monotonically increasing. So this looks completely different from the other one. And I'm emphasizing these things because maybe you heard an LLM generating the definitions or something else. And LLM could get the definitions wrong. So get it to define two completely different definitions. What if both of them are wrong? Well, we prove a theorem that if something is sorted, it's monotone. This took some work. And I prove another theorem that if something is monotone, it's sorted. Suddenly, I have a lot more confidence in my notion of being sorted. Because it's not merely, you notice that to get these two definitions equivalent to each other, it's not merely, I mean, of course, if they're both correct, they're equivalent to each other. But if they're both, if they're both wrong, they're usually still not equivalent to each other. They would not merely have to be wrong, they would have to be wrong in exactly the same way. Yeah. So that if you're proving equivalence of two different objects, whether the definitions or in work we are doing here at Emergence in SQL and whatever else, then things being wrong, both wrong and wrong in exactly the same way is quite very unlikely. So you can get a much higher level of confidence than you would get by tests, even if you don't have a ground truth. Simply by these kinds of proof challenges. I hear when I chat with people that there are other groups doing the same philosophy as well with other kinds of formal systems. Okay. By the way, there is one way in which both could be wrong in exactly the same way. They could both be getting decreasing lists instead of increasing lists. Okay. So you could guard against that by saying, and I did it, here it is. I prove that this list is sorted. Now this list is increasing, it's not decreasing. Okay, so the fact that this, so in addition to showing my two definitions were equivalent, I could generate concrete lists which I know are sorted and prove they are sorted. Okay, so all this becomes just too much of a coincidence to be correct. I mean, so that happens. Okay, so this is the philosophy behind a lot of the formal verification is not just where you know the ground truth. Ways of taking formal verification beyond where you know the ground truth. Okay, so I will now go just another couple of minutes over time by ending here. Okay, there's a lot of things as you see that I have skipped over. Working through Glimpse of Lean and LeanLang were asking us. I said I'll have a daily session where depending on what people request, I'll go into details of more and more of things here. Tomorrow we'll have a guest daily session of Ilya, and then the subsequent days this. And you'll just call me as you're looking at anything, ask for explanations. As I said, there are also line by line explanations. Here, I should both thank the summer interns who gave me the feedback that it was not usable without it, and also thank Codex, which actually filled in the line by lining. So in some cases, they were unhelpful. So I had to tell Codex that these particular things are unhelpful, give these kinds of explanations. It took 3 rounds, but Codex is quite marvelous, by the way, in case I did not mention that. Okay, so now, okay. So now, as I said, Lean is a programming language. Is it really? Okay. Can you actually run things in Lean? So this Lean, I have a binary file which compiles exactly the same code that I showed you. OA. Is that a directory? Uh, uh, no, that's an executable. Okay. Oh, I forgot to put slash. I put a space. Okay, silly me. Yeah. Okay, so that is an executable Lean. And okay, it got 100,000 elements in 80 milliseconds. Let's ask it to work a little harder. And so what it's doing is it's generating a random list and then it's sorting it. How about million elements? Okay, so this is with no optimizations at all. There are many obvious optimizations you can do. One of them is just use arrays instead of lists. I use lists because they're more elegant and it's easier to prove theorems, but you could prove theorems in arrays. And that increases by a factor of 4. You could also use concurrency, which is getting better and better in Lean. And there is a concurrent version of this here that will again increase it by a factor of 4 or so. Concurrency is not yet great in Lean. You often have to hand optimize, where in more mature languages, the concurrency is auto optimized. But anyway, I think 4 seconds for no, these are so milliseconds. 4 seconds for a million elements is not bad. I mean, you can call it. So what I want to, so maybe the ending conclusion of this session is that we saw theorems, we saw them being proved, and we saw programs, and they actually run. Yeah, and Lean programs actually run fast. Okay. Hi. So thanks all. We'll now have a coffee break. After that, we have the lab. Afternoon, we'll have first Deepak's talk, and then 3:30 we'll have Ilya's first demo talk.